Well, welcome to everyone who's joining on here. Give us just a moment. We're getting the recording set it up, hopefully, and then we'll get this thing kicked off. Excellent. All right. Well, thank you everybody for joining us again this morning on our second of 6 sessions, going through some of the improvements over NRECA and some of the work we've been doing. I'm going to be share my screen here really quickly just to kind of show you the schedule of events, kind of keep everyone on track on what's going on here. So last week we had our first session, which was the welcome and overview and just kind of some general information about Helix, and then we talked about improving T&D co-convergence using transmission and distribution tools, both commercial. That was pretty fun. All these videos will be available, so we are recording them as we're going, and then we will be putting them out on our YouTube channel to make sure that folks have access to them afterwards. So if you missed anything or want to review it, go for it. Additionally, we'll record these sessions today. It may take a little time to edit them and get them out there, but we'll make sure to make them available. So today's session is really going to be on a couple of topic areas of interest. One is some of the work that Anantha has been doing at NRECA to integrate Helix into the open modeling framework, which if you're not familiar with that tool, I'm sure that Anantha will give you a background on it, but it's a really phenomenal open source, openly available tool that has done a lot of really great integration work over the years. And then Phil is going to take some time and go through some of the Helix core developments. So we've had the last year, since we had our last users meeting, we've done a lot of kind of stabilizing the system, improving some of the ability to interface with it, and then just a lot of kind of really cool features that make it easier to use, both for scalability reasons and just as a general user. So Phil will go through all those kind of things today. And then you can see the schedule of events that we have for the rest of the month. Actually, really heading into March as we're going through the rest of the year here. I think these will all be exciting, so please join as many as you can. For those you can't, feel free to look them up on our YouTube channel, probably in a week or two. With that, I'm going to stop sharing. I think there we go. And I'm going to introduce Anantha from NRECA and let him take over control to start on his presentation here on his integration work.
Thanks, Jason, and good morning, everyone. Share my screen here. Okay. And can you see my slides?
Looks good.
Okay. So this presentation is about a case study that we did with Helix on simulating microgrids and mainly integrating that with NRECA's open modeling framework. So I will give an introduction to the OMF and give a background about how it works, and then the motivation for the case study, the Helix case study that we are working on, and I'll describe the case study and go into the details of the OMF model and show you some results that we've got so far. So the open modeling framework is an open source utility modeling tool that's freely available at omf.coop. It's essentially a visual front end for utility users to be able to use models without having to physically directly interact with the simulation tools or analysis tools, which generally have a high learning curve, a steep learning curve. So the goal is to build models on OMF that is essentially wrappers for analysis or simulation models that provide nice visual interfaces for users to interact with. And you see some screenshots on the right here that are some of the models, how they look through the OMF interface. OMF, in addition to that, also provides some visualization capability, some distribution and transmission network visualization capability. So if you have a GridLabD model, you can import it and visually interact with the model elements. It currently supports OpenDSS and GridLabD imports. And it's mainly used for financial engineering analysis for cooperative utilities. And it's also aimed as an environment where researchers can experiment with new models and encourage usage of research models without having to work by providing a more user-friendly interface. So the OMF architecture basically consists of a web-based front end and a Python-based backend. So on the backend, there's code and libraries and APIs that provide wrappers to interact with GridLab or OpenDSS models or some other tools, simulation and analysis tools. And for each type of model or case study or simulation, you can create a model that wraps the code around that, and then it can be visualized through the front end. And the front end is a web-based front end. The user interacts with it through a browser and is able to create an instance of a model and configure it for their case study requirements. They're able to import data from different sources. Like I mentioned before, they can import a feeder model from GridLab and things like that, and provides visualization of the feeders, graphs, and results, stuff like that. So currently, it supports these tools and libraries. So you can import windmill models and Sine-based GridLab and some transmission models as well, and some other data sources. And it has simulation wrappers for GridLab and OpenDSS, so you can run the simulation on the backend from the OMF code, and it supports some other simulation models as well. And the front end supports charting by using Plotly, so you can generate a chart and have it visually available on the browser front end, and the user can interact with that. And it also supports a distribution circuit editor where you can visualize a GridLab circuit and then select nodes and interact with it visually. So for this case study, so we had two basic motivations. One was basically the case study itself. Was the idea was to simulate the islanded operation of a microgrid using quasi-steady state simulation with GridLab with GridLab's delta mode, and to see sort of the frequency response during events during the simulation. And the other main focus was to integrate this model into the OMF so that the models can be executed and interacted with visually through the OMF interface. And this adds a lot of benefits to the OMF. OMF is popular with utility users mainly because it provides a more accessible front end, easy to interact front end. And so by providing the more advanced capabilities that Helix provides through a more accessible user interface, we believe that it'll be easier to provide more advanced simulation and analysis models to utility users by using multiple simulation tools. And another main advantage is that Helix helps us to decouple the controller implementation from the power flow modeling. And so a lot of these utilities have their distribution network models, which they use with other simulation tools. And if we can provide some other controller implementations as federates, and we can have a Helix core simulation, then it makes it more modular and allows the utilities to take advantage of additional capabilities and new implementations. So the goals for the case study are to simulate the islanded operation of a microgrid, and we do it using GridLab's delta mode, and we want to see how Helix interacts at those timescales with GridLab. And so the microgrid has distributed generation resources, and we simulate loss of generation and then what we can do to balance the load in case there's a loss. So there is a federate which implements a load shedding algorithm which works based on monitoring the frequency and detecting if there's a drop in frequency and shedding load. And then we integrate it with the OMF. The components are basically the distributed generation resources and loads, which are modeled in GridLab. That includes inverters and controllers for the distributed generation, and then we have a load shedding, a separate FedRate implementing the load shedding strategy. So here, this is basically the all the components that I just described. So you have the microgrid. Most of this is simulated using GridLab. We have a load shedding controller implemented in Python that acts as a separate FedRate that interacts with the GridLab model and communicates with the loads. It monitors the frequency and is able to shed loads. This can be extended by adding additional FedRates that can provide other types of control, such as controlling specific generation resources as well. So far, we have implemented a straightforward sort of load shedding algorithm here. So we use a modified IEEE 123 grid model which has some distributed generation added to it. We have some diesel generators at these locations and some inverter coupled generation. And we assume that loads can be shed individually. So the load shedding FedRate communicates with the GridLab model to shed individual loads in case of imbalance in the grid. So the power flow simulation is in delta mode in GridLab. So initially, one of the things that we wanted to do with this was to see if through Helix we can transition in and out of GridLab to have sort of a hybrid timescale simulation. So have a steady state simulation and then transition into a delta mode when there is an event happening in the microgrid. But we ran into some technical difficulties with our GridLab model. And so we were not able to do that hybrid timescale simulation. So the entire simulation was in delta mode. And so for the load shedding strategy, we took a simple approach that we'll monitor the frequency, and if the frequency drops by a certain value, then we determine that some generation has been lost, and we start shedding loads. We have a prioritized list of loads provided for the case study, and we start dropping these loads one by one at regular intervals, and then keep monitoring the frequency drop. And if the frequency starts to stabilize, then we stop shedding the loads. And I'll show you some visual results through the OMF interface. So now I'll show you the OMF interface. Okay. So OMF can be accessed at omf.coop, but I'm running a local server on my laptop. And when you go to the website, this is the main screen that you get, and you can create a user account and log in. And once you log in, you see some of the model instances that have been created for this account. So here, when you go to new model, these are the different model types that are possible to create for this account. And these are some instances. And I've, because it takes some time to actually run the simulation, I've already run the simulations and I have some model instances here. So this is one instance of the microgrid model here. So the models usually have a model input section and a results section. So the model input section allows you to select the name of the model and things like that. And you have an option to actually import a feeder model if you have one. And this part can be configured by the model creator. So in this case, I've created this for the frequency drop simulation for the microgrid. You can select a list of prioritized loads for your case, and then when you want the generation to drop, and then the frequency. So we check the frequency for the load shedding at certain intervals. So you can select what intervals the frequency is checked, and you can select the range to which the frequency is allowed to drop before a load is shed. And so right now, the strategy is frequency drop load shedding. So when the frequency drops to a certain value, we start shedding loads. It's possible to implement other FedRATs which implement other types of control. So, for example, if you have another FedRAT that say activates certain backup generation if capacity is lost, you could add a FedRAT to that. And so this is, I just added this as a dummy here. This is not actually implemented, but maybe if you chose something else, all of this could configure the way in which the Helix co-simulation is configured and executed on the back end. And so this allows you not only to set the parameters for the simulation, but also to select which FedRATs you want to run, what kind of strategies you want to simulate. And so for this case, don't pay too much attention to the actual values here. It's just for demo purposes and not very realistic for a real grid. But this is what it would look like. Is at this point, at the 3-second mark, generation is lost and the frequency begins to drop, and the algorithm starts shedding loads. And these red lines indicate times at which loads have been shed. And as after some certain number of loads have been shed, the frequency starts to stabilize and it stops shedding loads, more loads. And so here you see the list of loads and when the loads were dropped, and you can see this kind of information. So these yes. And so the same model can be run by reconfiguring these values for multiple options. So this is another case where I change the interval to 0.5 seconds, like check for frequency drop every 0.5 seconds and allow the frequency to drop a little more. And in this case, you see that it takes longer to stabilize, but fewer loads were dropped. And this shows the interval at which the loads were dropped. And so in the previous case, there were 8 loads dropped. And in this case, there were only 5 were dropped, but then it takes longer and the frequency drops even further. And then in a third study, I tried with some other values. And in this case, you can see that 6 loads were dropped, but the frequency stabilizes a little sooner. So this kind of this interface allows you to quickly try different configuring options, and then you run the model, and then you get the results, and then it allows you to make some choices, like if you don't want to shed too many loads, but you want to stabilize in a reasonable amount of time, then what are your different options? You can do some kind of analysis like that. So this allows the user to more easily configure and interact with the Helix co-simulation model. So like I said, the numbers were just for demonstration purposes, but we could possibly configure the actual power flow model itself to more accurately represent realistic scenarios, and that'll be more interesting for utilities, certainly. And we still have to work through some of the technical issues to implement the hybrid timescale that I talked about. That'll be valuable in this case. And I only showed the frequency drop based load shedding algorithm, but we'll look at implementing other types of control strategies, whether it's bringing up some other backup generation online or other types of FedRATs that can be included. That'll make the case study more interesting. That's the end of the presentation. So yeah, if you have any questions, I'll be happy to answer.
Yeah, Nanda, thank you very much. We do have a couple questions here. So Jing, I see you get your hand up. Go ahead.
Yeah, thanks. Hi, Another very nice work. Very impressed. Seems a very convenient tool to use to evaluate microgrid control modeling and other things. So I have 2 questions. One is, nowadays grid form inverter become a big thing. So many utilities put the grid form inverter in their microgrid, and they want to investigate the transient stability. Well, when the microgrid do the as learning operation, especially using the inverter as learning master. how the grid forming inverter interact with the traditional grid follow inverters. And so electromagnetic transient EMT simulation is a really important thing for the utility investigate. So I'm wondering if your OMF can do this kind of simulation to investigate the transient stability of the microgrid. Yeah.
Mm-hmm. Yeah, so that's a good question, with especially with this case study. So one thing is that the OMF itself is not a simulation tool and does not do any simulation or analysis. The OMF has other simulation tools that it runs in the backend, and you can choose which tool you want to work with. The OMF only helps you run it in the backend and then visualize the results in a front end. So in this case, actually, I used the model I used uses some grid following inverter models that were in GridLabD. There was some recent work coming from PNNL. I think Phil or I think some of these people might be in the meeting today who investigated grid forming and grid following models for inverters with GridLabD. I just used some models that I got from them, but they might be able to answer your question better.
Okay. Are they on the line?
Yeah, if you leave your email, I can forward a paper that they wrote, which looks at some grid forming inverter models for GridLabD.
Okay.
Yeah.
Okay. Yeah, I will do that.
Or yeah, my email address is here, so you can also directly contact me.
Okay. Okay. Let me note it down. My second question is, you say it's a tool for utilities. Can you give one example how utility use your tool and what kind of application they do? Just try to understand better the function or purpose of your tool.
Yeah. So there are some of the more older, more mature tools. Examples are here. So there is. So these are other tools that were created with OMF for the utilities, and so. So this one is a solar energy model. I'm trying to find one. There was one which kind of had this. Yeah, solar financial. So it kind of looks uses some simulation tools to determine how much energy a solar can get based on their region and the weather and things like that, and you provide your investment information and some parameters, and then when you do the analysis, it gives you some results about, for your purchase cost, what your savings are going to look like, what the generation. So these are all from other. I don't know exactly which model they use to compute these, but there are some models based on the weather information and just to estimate what their solar output is going to be over time. So it's this is what it looks like, and seasonal performance, things like that. So this kind of thing allows utilities to quickly provide what their investment limits are, what kind of region they are in, and what usage they have, and things like that. And so they can estimate whether it's cost effective for them to invest in solar and things like that. That's one example.
I see. Yeah, thanks. This is super cool. Thank you so much showing us this nice work. Yep.
Yeah, sure. Yeah, and you can develop an interface like this for your own model. If you have an interesting use case, then you can develop your own interface where you provide the basic configuration inputs in a nice interface, so that's easier for the users to enter the information, and they just do run model, and then you can visualize your results in ways that are useful for the end user.
Okay, understood. Yeah, thanks.
Now that we got a couple questions in the chat from Venkat here, I believe it's, is there any documentation listing various strategies available in present version of OMF tool?
Yes, so the OMF, actually, if you go to the OMF thing, there is a documentation page. It's that discusses some of the popular models and how to create new models and stuff like that. So it's actually well documented, and you can download the source code from GitHub, and you can have a local installation, and you can add your own models and see how it works. And of course, you can always reach out to me or to the OMF. There should be a contact information there, but you can reach out to me as well if you have any questions about working with the OMF.
And there's a second question here. Is there flexibility for historical data for financial analysis in the OMF tool? If yes, can you direct any documentation?
So again, like I said, OMF provides different options to import data, but it doesn't itself include any data. There are some example models which might come with some example data, like I think some of these solar models have already have some example data that are already there on the GitHub page or when you go to OMF. But usually our utilities use them with their proprietary data on their local system. So usually they have a local server that is protected, so their data is protected. But yeah, you will certainly find some example data in some of these models.
Just another minute or two here for questions if there are any further ones.
So this is Chris. I just wanted to say that I was really glad to see that OMF and Helix have found a touch point, because I think that it's a good force multiplier, and OMF is that approachable front end to complex modeling environments, and so anything that lessens the burden on the OMF back end for simulation to simulation daisy chaining and things like that is really a great contribution.
Thanks. Yeah, that's a good summary of our motivation actually. That and I think in the long run it'll really be helpful if we start using more Helix models.
It's yours for free.
Thanks.
Yeah, this is Trevor, the PNNL partner who worked with Anant on this, and yeah, part of the motivation in my mind from this was realizing, we PNNL have been working with NRECA and OMF for many years now, and often there are use cases they come to like, hey, our utilities, our constituents want to model this thing, and we have to go like, well, I guess we'll have to go add that feature into GridLab D, and it'll take multiple months, and there's only 2 people with enough knowledge to do that, blah, blah, blah. Now, like Anand was saying, with these controllers now linked in through Helix, written in Python, we're very optimistic that this is going to open up a lot more doors for different types of analysis that can be done that would be much harder to do previously.